Hey there, Jake. It's me, Michael. I was sending you this video because I haven't talked to you in a while, and I ran across something that I thought you would really enjoy hearing about. And since I am terrible at picking up the phone, talking on the phone, texting via a phone, really just any phone-related activities, I decided I would make you a short video. And if you like it, then yippee. If not, then just don't bother responding to it. But anyways, I wanted to send you this video to kind of talk to you. I hadn't conversed with you in a while and get your opinion, thoughts on I don't know, spinal cord injuries and this fellow I heard about called Dr. Gregoire Courtine's experiments in working with them. But anyways, spinal cord injuries. You know far more about this than I do, but I'm just going to kind of run through quick overview of kind of where I am in spinal cord injuries. But essentially, from what I can understand, went ahead and made this diagram. But yeah, right here's our brain. In order to move anything, we have essentially a motor pathway that connects out, and whenever our brain sends out a signal, say to move our arm, it travels down from our brain, synapses at a point in our spinal cord with another neuron in the ventral horn of spinal cord disc level, which then moves out and synapses at the muscle or well, exposed at the skeletal muscle that it is supposed to connect to, which will cause it to move or to change its movement some way to relax. Essentially, electrical stimulation causes stimulation of the muscle, which causes contraction. And through just thousands and thousands and thousands of these neurons connecting the pathway is how we get all of our motion and all of our skeletal somatic pathways. And that is essentially what I understand to be the way we move, voluntary, our voluntary movement. Now, if we were to suffer some sort of injury, say, we were similar to Christopher Reeve, we were out riding a horse, we fell, and we had an injury that caused trauma right here on our spinal cord, it stands to reason that anything that connects underneath this, any nerves, any neurons that are severed at this point would no longer be functional, causing paralysis of essentially the entire, say this is at the mid back, anything lower than the mid back, or it could be even higher up, because I know that neurons generally stretch down because our spinal cord doesn't reach as far down as our spinal column. So we end up with paralysis and the inability to move anything else down here. So essentially that's how paralysis is caused. It causes a break in the motor pathway as we know it, as I know it. Just let me know if I'm off here anywhere. I'm kind of working through it so that I can kind of learn it as well. Make sure I've got it right in my mind, because I kind of run across the problem where that I'll think I have it in my mind and then I say it to somebody else and they're like, that is absolutely not what is going on. So this right here is my marker not working, but this right here is our break. Let's say it's not a complete separation, but essentially we have a trauma here that cuts off communication between your brain and your other portion of, or down here, our other portion of our motor pathway. So what we have is our neurons connecting to our brain are cut off, but we still have this sort of reflex, the second section of it that is still connected. But I guess from what I've been looking at, whenever we have damage to an axon, whenever damage to a neuron, we undergo what's called anterograde degeneration, which essentially says that any place distal to where the damage occurs compared to the cell body will begin to degenerate following the trauma that breaks this neuron. So at the moment that this damage occurs, there's sort of a ticking clock that this neuron here, I mean the anterior portion of the neuron is still going to be acting fine, but this distal portion is going to start to degenerate. And where we find, we have damaged neurons, on like a daily basis, on a secondly basis, I assume. And essentially, what it does is we have a break in this axon, and this part of the axon is able to grow and connect with the broken part of the axon. If I remember correctly, this part of the axon sends out. Well, I think it's the Schwann cells or the oligodendrocytes send out chemical messengers, cytokines that attract the growth of this part of the axon to attach to the rest of the cell, reconnecting and fixing this damaged neural pathway. However, if we like here have a severe trauma, the distance is essentially too great for us to fix. I mean, for this part of the axon to find its way back to this part of the axon and fix it. So essentially, this entire section of our pathway disappears, gone, just disappears, gone, and results in paralysis. So that's kind of where my idea of paralysis. And from when I've kind of figured, I have no idea if this is right or not, but our general idea behind treating spinal cord injuries is to try and induce the growth here back and reconnect with the other part of the axon before this section degenerates, and that's sort of where we are, which makes complete sense to me. However, this fellow, Dr. Gregoire Courtine, I can't remember his name. Sit down. He's I think he's Swiss, but he's doing Swiss research, and essentially what his research is he takes a rat, and I have no idea what I did with my cap here, but oh well. He takes a rat and he severs his spinal cord in two positions, inducing paralysis. And what he was able to, I mean, what he said was, hey, up here, down here, we still have a functioning sort of locomotion network. Like we have our neuron here that connects out to the tissue. That should still work. I mean, this isn't an instantaneous degeneration. Should still work if it is properly stimulated. So what if instead of trying to regrow this right here immediately, we go ahead and we sort of inject like a pharmaceutical cocktail of the proteins and neurotransmitters and I assume whatever else is sort of that this part of the pathway is no longer receiving from this part of the pathway to preserve this, and then we can develop our own sort of device that can go in and stimulate this electrically. I guess he calls it a neuroelectric prosthesis, I think it is, something along those lines. But the idea is to go in and stimulate electrically these neurons, and that way it essentially allows your muscles to react without any input from your brain. So he went ahead and developed these devices, and what they found was that rats that originally were not able to stand, not able to use their lower halves in any other way, think Christopher Reeve here again, were now able to stand on their own weight, and even he would put them on a treadmill, and the rats could respond to the stimuli with just this part of their spinal cord, and I assume his neuroprosthesis, to be able to walk. However, they were walking, but they were not walking voluntarily. It was completely down here with the prosthesis, with the reflexes, and there was, they were walking. And I've seen similar stuff in humans where it's sort of like a complete computer generated. I'm walking, but as you can see, it's sort of a limited. It's good for you to be able to stand, good for you to be able to walk, but you would like to be able to do this better, where you'd be able to completely voluntarily just walk again. So I guess his next step was, so we've developed all this motor function down here. However, we have no connection up here. So with the rats, he went ahead and I guess he attempted to motivate them via I guess Swiss chocolate. He just they decided, okay, we have all this going here. Maybe if we provide the proper motivation, proper stimuli, we can redevelop voluntary control. And eventually, he was successful. And as you can, I mean, the rats were completely able to walk on their own. I mean, not completely, but they were able to send uh, send signals from their brain to allow them to walk with the aid of several devices. But they were able to reestablish a degree of voluntary control of their lower extremities, which is just awesome in my opinion. I don't think it's ever been done besides from this. With this degree of spinal cord injury, I mean, at this long after the damage has occurred, but I'm just gleaning what I've read and sort of gone over in my head, and I guess I've been sort of researching a little bit, but I have no idea. I mean, this is just me kind of working through it, so let me know if I'm wrong here. But so essentially, they were able to walk again, and the way they were able to was that somehow this, when given the proper motivation, these spinal cord, you know, fibers, I assume were able to reattach. But he talks about how there was complete new development of 300% more fibers were projected down and created from up here in the brain and passed through the non-damaged portions of the spinal cord and reconnected down here. Now I'm not 100% how that worked, but the idea that if you are given the proper motivation and with this here all preserved and working involuntarily, that you're able to eventually over time and with great effort and great motivation able to re-establish a degree of voluntary control after being completely rendered completely paralyzed is just completely interesting understanding, and I probably have completely fascinating, and I probably completely butchered this, but I'll leave you a link on the videos and his website, but pretty freaking awesome if you ask me. So that's kind of the way it is, and he sort of goes on in conclusions that I really like, and kind of leads me there. I'm like, whoa, cyborgs in the future, but he talks about the completely new field of neuro prostheses that are not designed to control, from computer input control. I guess they're not designed to completely allow you to walk involuntarily, but instead designed to help your brain and your nervous system repair themselves. So instead of replacing it, it's the idea that these new prosthetics can be placed all over all over wherever you have nerves, wherever you have neurons. It can help your brain fix itself and even work better. So that's kind of that. But hey, I wanted to say hi, buddy. Say hi to your wife. I figured this is a good way to get in contact with you. And I don't know, remember old days of hanging out and talking about the most random science stuff in the world. But this is kind of where I am. Let me know what you think. I had kind of a good time, drawing my little figure here and talking through, and hopefully I've learned something, and hopefully you'll learn something too. But anyways, whenever you get time, anytime, just watch this and let me know what you think, and I will attach all the information that goes around with this, and hopefully I can see you soon, and hopefully all your studies are going well, and I hope you're doing just awesome. But thanks for listening. Bye.